to my scientific supervisor, Anna Zapaichikova, for her support and unwavering motivation throughout the course of this project. I would like to also acknowledge the members of the CanLab laboratory, the Zhenjun Ye, the Elvira Yang, Francesca Musa, Divian Shutak, Reza Mohamed Yast, and our laboratory leader, Benjamin Khan. So today I want to first motivate the reason of our research, state our research questions and our contributions, then describe our solution, the results that we obtained, and evaluations. Then briefly talk about the limitations of our work and make conclusions. So first and foremost, why we do this research generally is that the pediatric cranial muscle assessment can provide valuable insights into children's development and early detections of neuromuscular diseases in pediatrics. The instruments that can hypothetically tackle those challenges are CT segmentation tools, which are well explored, but unfortunately they are not recommended to use in pediatric applications because of ionizing radiations, which is prohibited for developing organisms such as children. And of course, we could possibly annotate the data set of pediatric data set for segmenting MRI, but the manual annotations of those 3D volumes are very time-consuming and requires the expert radiologist knowledge, which is also the expensive. Therefore, we pose two main research questions. First, is it possible to use already developed CT segmentation tools to segment the MRI volumes without manual labeling? And second, is it possible to use the model trained on the adult population to segment the pediatric scans? Our contributions include the methodology that we proposed, implemented, and validated, the segmentation model that we will make open source soon, the corresponding dataset, and the novel defacing algorithm. To address our research questions, the cornerstone of our solution became the SYNRAD 2023 dataset, which consists of two tasks and two medical imaging modality pairs. From them, we selected only the first task, which is on the cranial structures, and we selected the MRI CT modality. The distribution, the ages of the patients in this cohort starts from the age 18 and ends with age 92, with the mean age of around 55. And the split between the male and female parts are 43 to 56, even though after the manual filtering of those samples, the distribution became more even. So the whole subset consists of 180 samples. We manually reviewed all 180 samples and removed 25 samples that on which were present artifacts such as noise, motion blur, and missing MRI parts. Then we took those 154 samples and we registered them. So those pairs were already co-registered one to another, and we also registered them using our algorithm that developed in the previous work. Then, based on this data, we proposed and implemented the following pipeline. So the first step is to we use the total segmentator segmentation tool to create the pseudo labels for the CT scans. Then we consolidated the labels to speed up the training and inference process of an NNUNet. And then we trained the NNUNet to predict the CT pseudo labels directly from the MRI scans. Then, to ensure the patient's privacy and unbiased evaluation and unbiased attitude during the evaluation process, we developed the custom defacing algorithm, which works in the following way. So consider the MRI volume V and the corresponding binary brain mask of the same size. Here the volume V is the gray part without the green segmentation, and the brain mask is the green mask here. Then we define the so-called top point, which is the maximum for each Z slice. We define the top point, which is the maximum X coordinate in which the brain mask is still present. So in other words, if we will move the line from top to bottom, the first point at which we touch the brain mask will be the our top point, which is here for this example. If there is no brain mask present on the slice, we define the top point as 0. Then we use this top point to define the adjusted top point, which is the maximum between the current top point and the previous adjusted top point. The idea is that the adjusted top point can only move in the anterior direction, but on the posterior when we move from inferior to the superior slide. And to make this algorithm deterministic, we also define the initial value as 0. Then we for each slice we remove the pixels from MRI and from the predictions that are below the adjusted top point. Here we can see the results of work of our algorithm on the left, and the corresponding defacing of the predictions of our model on the right. As we can see, after some point, which is the low point, the top point doesn't move in the posterior direction, meaning that they remain here, so we don't lose the valuable predictions. And the correspond in the similar way we deface the MRI scans. Here we can see the predictions of our models in the XY slice. At this moment, we were quite surprised that the temporalis muscles and the brain was quite well segmented, like from the observation. Therefore, we decided to move on with to validate the predictions of our model. So for that we composed the evaluation dataset of 6 smaller datasets. which is Calgary, ICBM, IXI, ABCD, Baby, and Pink dataset. We sampled from all of them, we sampled 50 samples, which were stratified by sex, by age, and by dataset. And we composed those 50 samples, and we call those 50 samples the mixed dataset. Then we coupled this mixed dataset with the broad space datasets. On the picture, the red color indicates that it is the dataset of the tumor cases, and the blue dataset means that there are only healthy cases. Then we merged those two datasets into dataset number 1. We also took a CREAN and CURMAP dataset and combined them into dataset number 2. Then we use those two dataset number 1 and dataset number 2, to first validate our defacing algorithm, because the defacing algorithm is used in the further validation experiments. So we first validated the defacing algorithm itself. So we took each sample from those two datasets, like the predictions on those two datasets. We rotated each prediction by 5 degrees. And then we defaced both the 0-angle cohort and the 5-degree cohort, and compared the corresponding volumetrics of the predictions. Therefore, we arrived to the following results, which is the first row in each cell. It is the mean absolute deviations plus minus the standard deviation, the percentage deviations, and also we run the two-sided Mann-Whitney U-test with false discovery rate correction to check if the 5-angle cohort significantly deviates from the 0-angle cohort. And we then observed that the p-values for each were higher than the significance level of 0.05. Therefore, we concluded at the stage that the defacing algorithm does not impose the significant volumetric deviations, and it can be safely used further for the validation experiments. Therefore, we moved to the validation of to assessment of the acceptability of predictions of our model. So we took the dataset number 1 samples, which, remind you, were 100 samples in total. We ran the predictions of TissueNet model on that pack of samples. Then we provided the corresponding results to the 2 non-experts and asked them to evaluate the predictions, segmentations, using the 5-degree Likert scale, which were acceptable with no changes, acceptable with minor changes, bad image quality, unacceptable and not visible, and unacceptable with major change. Then we aggregated those ratings into 3 bins: acceptable, bad image quality, and unacceptable. And for each sample for which the ratings were in disagreement with correspondence to those bins, we provided to the expert radiologist who made the final judgment. The radiologist, by the way, was asked to make the same predictions, and we also bin those predictions from the radiologist in the same way as to those raters. Then we analyzed the results by measuring the GWAT-AC agreement score between the raters. From the table, we can observe that in general, the agreement between raters are quite good for fat and muscle, but not always good for the school. And the general acceptability ratings say that the raters agree that the 989 predictions of the TissueNet model was acceptable and 10 unacceptable. And by observing these results, we moved to the second validation study of the predictions of our model. So we took those two samples of the dataset 1, of the dataset number 2. This is the important point. We run the total segmentator on the on those scans, and created the pseudo labels basically. Then we provided those pseudo labels to the expert radiologist for correction. Therefore, we obtained the ground truth for those 10 scans. Then we run the TissueNet and Grace model on those two samples, and compared with the ground truth from the radiologist. Then we measured the discrepancy between the ground truth and TissueNet and Grace model predictions with the DICE score. As we can see here, the TissueNet outperforms the Grace model in pretty much all the labels, except from the fat. For the healthy population, at least for our sample of data. But if we look at the Hausdorff 59 percentiles of Hausdorff distance, the model TissueNet outperforms Grace in all labels. In this moment, we were quite happy with the results, and but even though the results are quite good, our work has some limitations that are still not addressed. The first thing is that the model generalizability to the fat-saturated MRI, because as it is known, the T1 weighted fat-saturated MRI suppress the fat signals in the MRI, and we have not validated our model on the fat-saturated MRI images. Therefore, we cannot guarantee that this methodology will segment well subcutaneous fat in the T1 weighted fat-saturated MRI. Second is the possible model degradation under extreme conditions, because we have not validated how the model will perform in cases such as artifacts like motion blur, noise, missing pairs, missing parts of the MRI, or for example, the skull surgeries, which is quite prominent in the MRI images. Also, we do not guarantee that we have not validated our model if our model will work in the other domains. We validated our model on the cranial domain, but we still don't know if the proposed methodology will work in the domains such as pelvis and the upper body parts. And even though the expert radiologist assessed some of the labels, we still don't know how the model will perform in the real-world clinical applications when there are maybe side cases for which it may not work. So in our work, we we answered two research questions. The first is we showed that it is possible to use CT segmentation tools to segment the MRI volumes. The second is that the model which is trained on the adult population can be applied successfully to the pediatric population. We developed the methodology. We created the open source pediatric MRI segmentation tool with the corresponding datasets, which is our three contributions. Our future research will emphasize the following. First is how our 3D volumetric UNET model will perform compared to the cross-sectional model, which was addressed in which was studied in the previous research. Second is the extensive clinical validation of our segmentation model and how well it will perform, to assess how well it will perform in the real clinical cases. Also, we plan to explore the other domains, such as pelvis and upper body parts, and how our methodology performs in those domains. And also the creation of normative growth of pediatric normative growth charts. So I want to thank you for your time, and I'll be honored to answer your questions.
Thank you, Markіян. I would start. So I have an impression that you have a good understanding of the problem domain, but I would like to understand your contribution from the data science and computer science standpoint. Could you please summarize your contribution in the context of the data science and computer science? So what did you do in this work in the context of computer science?
So can I answer in English? Okay. So our main touchable contributions is the segmentation model, the dataset, and the novel defacing algorithm, as well as the methodology.
So segmentation model is you used existing architecture and trained it on your data set. So is it a new segmentation model?
It is not any novel segmentation model, but it is the trained model that will make open source after the publication in the journal.
Okay. And what is the new data set? Could you please remind me? So as far as I understand, you created pseudo labels and then used them for training, or correct me if I'm wrong. What is the new data set?
That's right. So the new data set is the one which was mentioned. It is the data set number one, for which we created the pseudo labels and performed the acceptability testing. So,
and do I understand correctly? So, you created this data set, and then there is an NN-UNet model with like existing training setup, and took that setup as is and run the model on this data set? Or you maybe, I don't know, adapted something or something like that?
The NNUNet model was took as is. Actually, it is quite common in the medical imaging in sense that if we compare, for example, with the total segmentator, okay. So the total segmentator study, they also used the NNUNet. So the total segmentator is also NNUNet, which they trained on the
Okay,
data.
thank you. And my last question, you listed a lot of like people in acknowledgements. Could you please elaborate a little bit more? What was specifically your contribution? What was the contribution of your supervisor? And what was the contribution of the team that you mentioned in scope of this work?
Okay, so I will start with my contribution. My contribution was the implementation part and all data engineering and coding part. Anna Zapachkova, my research supervisor, she managed the communication with the radiologist and experts in the Massachusetts Brigham Hospital. And other team members, they just contributed some thoughts about what we are doing on the weekly meetings.
Okay, thank you. I'm done with my questions.
Can I proceed? So, Markіян, I want to jump back to the question regarding the model architecture you used. So I didn't find in your master thesis any arguments of selecting this model. You didn't do any evaluation of other existed models. Why is that?
According to in one research that unfortunately I didn't mention in my thesis directly, the researchers evaluated several models, how they perform on the different domains in terms of the different body parts, segmentation models, I mean, and they found out that the NUNet scored top 1 on the 7 out of 10 tasks.
Okay, I want to bring you critical thinking here. So you mentioned that there is one paper, and you even not mentioned it in your thesis. And in this one paper, someone evaluated different 7 models, and you just accept their decision to make your research. I'm not sure that it's correct way how to conduct research by a master student. Do you see what I mean?
Yeah, I see. But I also communicated with the researchers of our team to.
And they said that it's okay to use.
How many of them are ML engineers?
Okay. One question further.
Yeah, the same question, right?
Yeah. So the researchers there, they are specialists in the computer science, as well as they have knowledge in the
But they were okay
medical
that you
domain.
used just some paper and bring that model from that paper, and that's it. Have you attended master seminars?
Yeah.
Okay. Then can we get back to the data set? And you mentioned that so there is like a bunch of those blue data sets, and then at some moment you integrate these red data sets, and as far as I understand, it's deceased, like with tumor. Is it correct?
Yeah, the red data set consists of the tumor cases.
And I'm not sure how it's aligned with your main goal of this work. How does the data set with the tumor help you to solve the main goal?
Yeah.
As far as I understand, the main question was how to transfer from MRI to CT.
Yeah.
And how does this tumor data set how can this data set help?
Okay. So we wanted to assess how our model performs on different type of cases, not only on the healthy patients, but also on the tumor cases, because generally the people do that that go through the routine scanning, they are not usually healthy patients, but those that are in the suspect of having, for example, the tumor. Especially, this is especially relevant in the Massachusetts hospital in which this model are supposed to be launched. So therefore, we assessed if our model performs well on the healthy as well as the tumor case.
I'm curious whether you found on literature such approach. It seems like you just took a bunch of data sets, put them in one bucket, and then decide, hey, let's train our model on everything we have on the market. Can you get back to the image when you explain us this facial removal, or how you, with those, yes, the previous one. Yes, this one. Okay, this one. So what's going on here? This rotation for 5, yeah, so why do you do this manipulation?
Okay, so during the validation studies to assess the model performance that were after that, the facing validations, we used the registration algorithm, which actually tilts the MRI scan forward and backward. And we wanted to make sure that this does not, so that our defacing algorithm does not interfere with the registration algorithm.
So there is some physical process with which what is going on? It tilts the MRI scan, right?
Yeah. So the
and for this 5 degrees, so why 5, not 3, not 7?
Because it is the as we measured, it is the average degree on which the registration algorithm steal the MRI scans.
And can you get back to the slide number 15, probably the next one? Yes, and what are those numbers on the first row and those deviations? Because if I see those, so what are the measurements?
Do you mean?
Yeah, this one.
So
is it okay to have a negative value here?
It is the standard deviation. So
yeah. So
this
could this, so if we have this 37 minus 50, we will get negative value. Is it okay to have negative values?
Okay. So yeah, in general, it is possible to get the negative value, because if you tilt the MRI scan, you actually can expose most the labels
So
that
what are the
were
values? So what
behind
is the measurement of those values? This number 37. So what is this?
It is the
unit measurement. So what is
it? It is the mean of absolute deviations of the volumes.
What volumes?
Of
Volumes
the
of what?
the labels of the label volume. So the each prediction consists of voxels. In our case, the one voxel corresponds to 1
volume,
millimeter
and volume
cubic.
Can volume be negative?
It is on the table. It is the volume deviation.
It's deviation.
Yes.
That is,
Yeah.
that's a bit counterintuitive.
Okay, problem done here.
Just to elaborate a little bit more, is it a 3D setting or a slightly 2D setting?
Uh,
I mean, in the previous
the-
slide,
oh,
this validation setting, is it a 3D setting or a 2D setting?
it is the 3D setting.
3D, this is what volumes, right?
Yeah.
Okay, so let's go to my questions. In slide 7, could please go back to slide 7? You mentioned that training data set contains 154 images, right?
Yeah.
Samples. As a statistical representative?
It may seem a small data set, but we should also consider that each sample is the 3D volume. So it is not the simple 250 by 250 image, but each sample is like 500 such images on average.
I'm about the individuals to which the images correspond. Is the subpopulation which has been imaged, MRI'd or whatever, or CT'd, statistically representative in what way?
It is considered the average size data set. So
Okay. Then could you please, yeah, go forward to slide 8.
9.
8.
Okay.
8. Why 8? Here, yeah, this question has already been posed. What were the reasons to choose the and then UNAT? You answered somehow. Then please go to your slide number 17. This is the splitting ratings. We have 89% for acceptable. We have 10% for unacceptable. Where 1%, missing 1% goes to
It is
bad quality.
Yes, that's right.
You didn't mention it here.
Because it was 1%, it was pretty much not visible on the slide. So this thing
You see, the scale is 100 and percentage scale is 100. So
yeah, I see, but
this could be improperly interpreted by a not very attentive listener.
okay, that's the good point. The thing that why we only show the acceptable and unacceptable is because we measure the raters agreement using the acceptable and unacceptable, and the bad images were removed. So in this table, the measurement is between acceptable and unacceptable, like binary classification. So therefore, we did not draw the how this 1% of bad images here, because therefore one can interpret that the tables also included the measurement by the
It was implicitly clear for me as well. Just for making it more clear, I would make the scale from 0 to 99 in that case. But it's okay. And one more question about your evaluation data set. Yeah, this one. Do you think this evaluation data set is balanced? And if so, on what parameters it is balanced, on what it's not sufficiently balanced?
So the dataset number 1 is balanced on the patient status, or tumor and versus healthy, the sex, the age, and the that's all.
A table showing these parameters and statistics would be very helpful in terms of proving the balance. I mean, this slide has a space for that.
Agree.
Thank you.
Thank you for your presentation. Could you just clarify one more moment? You use total segmentator to produce some labels, right? What do you feed to your UNet model? This result of this total segmentator, right?
Yes, after the label consolidation.
This total segmentator has, I believe, his intrinsic error, right?
Yeah.
And then your total pipeline error of this total pipeline, it's this total segmentator error plus UNet error, right? So
Yeah.
could you estimate this result of generative of these, say, the labels, or separate result for you mean error of the total segmentator and error of the UNet?
Okay, so you're right. The total segmentator have some its own intrinsic value in addition to the NUNet, because basically it is the NUNet error plus their NUNet error plus our NUNet error. But therefore we measured the error during the second validation study.
Can you measure the error of this total segmentator? Maybe it's a known solution, maybe it's known value.
Oh, okay.
I'm just curious.
If I understand,
How reliable your data, input data?
Yeah, like isolate the error of the total segmentator on our dataset. That's the good point, but we did not conduct such experiment. We focused on the end validation.
You just believe that it's good. Okay.
I have a very short question. So Markіян, one of the objectives of your work is to answer the question, can a model trained on adult imaging data be effectively adapted for pediatric cranial structure segmentation? I didn't hear anything about this transfer possibility.
Okay.
So you, as far as I understand, all data you trained your models on were for adult populations only. How can you be sure that the results on these data set can be transferred to the quite a different population of children? They have different physiological and just yeah, it's a different population.
Yeah, that's why we address this question. So the synthread data set consists of cohorts starting from age 18. Therefore, there's the adult population. In our validation studies, we use the data set of pediatric cohort.
What was the pediatric data set?
With
Could you please recall us to have it on your slide? Where is pediatric?
Okay, so the broad space is the pediatric dataset. The mixed dataset is actually a mixed dataset of pediatric and adult population. A Korean and CareMap is also the mix of pediatric and adult populations.
To elaborate it a little bit more, in your tables with results, you do not outline the pediatric use cases, and you do not compare those with the adult population use cases. Why so?
Yeah,
This comparison would directly answer your research question.
yeah, that's right. The tables that are presented during the validation studies, they are on the mixed cohort, not the separate one. So yeah.
To be sure, a mixed data set consists of 50 objects, yes?
Yeah.
And you said it is balanced.
Yes.
So it means that there are maybe 5 children in the data set?
Why so? Can you?
On age category.
Colleagues, I think it's not question answering anymore, but discussion, and we can move it to the break. Thank you for active QA session, and let's continue. Thank you, Markіян.
Thank you.
So, as you can see, master defense Q&A can be quite hard, but that is part of the
Is this hard? Just like
So sorry, I will introduce you.
Thank you.
So let's move on. The next work in this block will be presented by Wікторія Маковська. She was supervised by Микола Трохимович and Diego Trumper. Mikola is the graduate of this program, and Diego is professor, teacher here too. So it's pleasant to see this work. Wiktoria will be presenting her work entitled Vandalism or Knowledge Manipulation, Detecting Narratives in Wikipedia Edits. Please.
Thank you. So I'm here happy to present to you our work dedicated to detect knowledge manipulation in Wikipedia revisions with special focus on Ukrainian and Russian Wikipedia. We also aim to investigate if vandalism and knowledge manipulation itself has common grounds inside Wikipedia, or it is a distinct phenomenon. So my advisors, Mikola and Diego from Pompeu Fabra University, and I'm deeply thankful to them for helping me with advice and strict feedback to shape this work. Our approach is based on detailed analysis of changes made in Russian government-backed fork of Wikipedia, created to reflect Russian state point of view. We apply a system to Russian and Ukrainian Wikipedia to check if such manipulative edits are present there. We showed that models developed in this work can be effectively applied beyond Wikipedia as well. And now I'm going to present motivation and background behind the work, our approach to solution, and final results. So Wikipedia is among the most widely used knowledge source on the web. According to Wikimedia statistic from beginning of 2025, most views from Ukraine goes to Russian Wikipedia. And Ukrainian Wikipedia is only on the second place. Moreover, Russian Wikipedia version is also popular in Germany, US, and other countries. With taking that into account, we acknowledge that investigating Russian and Ukrainian Wikipedia for knowledge manipulation detection in a given setting is a priority. Also, recent investigation by NewsGuard revealed that Russian state-backed campaigns deliberately flooded internet with over 3.6 million articles with propaganda in 2024. As a result, top 10 generative AI models started to mimic Russian disinformation claims in almost 32% of the time. Researchers do not specify which models they tested. They keep it anonymous and just say that this tactic is now referred as LLM grooming. And since Wikipedia is also widely used in machine learning and especially in natural language processing, it becomes a target for those who want to manipulate AI outputs as well. So certain Wikipedia pages are obvious targets for manipulation due to their controversial or sensitive content. A notable example is Melitopol page, sorry. At one point, Edit claimed that Melitopol is a subject of Russian Federation. This assertion was reverted since Melitopol is a city located within Ukrainian territory and recognized by international law. Our work aims to detect such revisions and conduct an analysis of their nature. In June 2023, Russian Wikipedia fork was created to align with Russian state narratives. It captures a selectively created version of Wikipedia content, modified to comply with government regulations and ideological position. This makes fork a unique resource for studying knowledge manipulation itself. Since fork originates from an older snapshot of Russian Wikipedia, direct textual comparison between Russian Wikipedia and fork itself could help us isolate semantic differences, detect removed, inserted narratives, and generate labeled pairs of manipulation for manipulation detection. This dataset forms the core foundation for our training the knowledge manipulation detection model. But before we continue, we have to define what is knowledge manipulation in this work. We define knowledge manipulation as an intentional attack on knowledge integrity to impose a specific framing. In the context of Wikipedia, knowledge manipulation is deliberate violation of neutral point of view policy that all Wikipedia articles should follow. This includes any effort to substitute terms, to distract from the original meaning, reshape statements to appear ambiguous, mislead readers by removing specific details or adding statements that can create bias or biased framing. We also define narratives as recurrent patterns of edits that conduct a particular interpretation of event or identities over time. Here are the examples that we have discovered during this work, and this illustrates the previous statements. Given words, we were repeatedly substituted. So as you see, war to conflict, occupation to presence of military personnel, annexation to return to, and armed invasion to military operation. Investigated type of knowledge manipulation operates in gray zone, meaning that those who want to do these injections, they exploit Wikipedia collaborative framework and nature. So malicious actors may inject modified narratives, but at the same time, they can avoid being detected by human moderators or by automatic vandalism filters as they initially attempt to comply with platform rules. Let's take a closer look at how Wikipedia reflects contested narratives using this page, so-called special military operation, as an example. On the left, you see description from Russian Wikipedia fork. So they state, special military operation is military actions in Ukraine that began on February 24. Then we, in the middle, show an injection of similar language in Russian Wikipedia. They state that SMO is Russia's invasion of Ukraine, which began on February 24. At the same time, that in the middle, this is the version which once were inserted into Russian Wikipedia, but then it was reverted, and it was reverted to this final text. Special military operation is a propaganda euphemism introduced by Russian leadership. So what's important for us to see here that current Russian Wikipedia version defines this term as propaganda euphemism. And they are not trying to legitimize Russian government statement about military operation. And that is important for us because we want to make sure, we want to see this in official version of Wikipedia and avoid or spot attempts of injections like in the middle. So to understand research gap, we investigated main works and data set listed in the field. On the horizontal axis, we move from fact-checking to manipulation techniques, propaganda, and finally vandalism. On the vertical axis, we see types of data set based on the source where we took it, where people collected and took it. So these data sets that collect media, from social networks, and also edits from Wikipedia. Most existing data set focus on media and social networks, meaning like news sites or news articles and posts in Telegram or X or Facebook. They also target misinformation and propaganda in journalistic and social context. Moreover, recently, UNLP 2022 shared task revealed also additional data set to cover detection of manipulation techniques in social networks. But at the same time, we can see that there were no data sets which could assist research in direction of propaganda detection or manipulation technique detection inside Wikipedia setting. It became possible only thanks to the work of my advisor as well, Mykola, and others who collected Russian Wikipedia fork dataset, and it will appear soon available. So we use this Russian Wikipedia fork dataset as a ground for our research. But on top of that, I also highlight propaganda corpus, which collects Telegram posts and created by Veronika Solopova and the others. I highlight it here because we used this data set to try to understand if derived methodology could be applicable beyond Wikipedia as well. The research explores whether, so I want to set up three main research questions. We explore whether knowledge manipulation sources can help us detect manipulation across languages and platforms. So research question 1 asks whether edits in Russian and Ukrainian Wikipedia resemble patterns found in the manipulative work itself. This may help understand if manipulation is already leaking into official Wikipedia versions. Research question 2 goes a step further. We want to ask if we can actually train a model on the manipulated fork and use it to detect similar manipulation in regular Wikipedia context. And research question 3 explores generalization. If the model works on Wikipedia, can it also detect manipulation in other settings? For example, like help with vandalism detection, or, as I mentioned, help with manipulation detection in other contexts, like social network posts. We also used in this work Russian and Ukrainian Wikipedia edits datasets which include all page level edits between 2022 and 2024. It includes editing activities related to both neutral and sensitive Wikipedia pages. Sensitive pages are those which may trigger discussions about, for example, Russo-Ukrainian war, territorial status, historical events, or in general can trigger editorial disputes or edit wars. This data set from 2022 to 24 contains metadata such timestamps, page titles, and which is the most important for us is revert status flag. This flag indicates if current revision was reverted by moderator or it was not reverted and it's okay and it's probably going to stay like this. So this is the second data set which we used to make sure that we can find insights when comparing with Russian Wikipedia fork dataset. Here is our proposed methodology. At first, we start with dataset analysis. It is done with an objective to define edit patterns and compare it with Russian Wikipedia fork. Like we apply Jensen-Shannon divergence, Levenstein distance, and TF-ADF score calculation. Next, we, in the model development stage, we work on knowledge manipulation, binary classifier, which is fine-tuned on fork dataset. We also created vandalism BERT-based classifier fine-tuned on Russian and Ukrainian Wikipedia dataset by usage of the previously mentioned label, which is revert status flag. To conduct evaluation stage, we have prepared holdout dataset in advance, which is really important because this dataset includes revisions after September 2023 to make sure that there is no data leakage, which could happen if we use revisions that will met both in fork and Russian Wikipedia. As I mentioned, fork is a snapshot of Russian Wikipedia at some point in time. So if you take data before that moment in time, we can end up finding super similar edits. On top of that, we prepare propaganda corpus dataset, which was originally introduced by Veronika Solopova, as I mentioned. In a nutshell, we propose to compare two classifiers. One classifier is trained only on vandalism semantic features, and the other metadata features as revision by its diff. The weak supervision is done by selecting revert flag as target label. And as revert flag normally indicates if revision contains vandalism in terms of Wikipedia setting, we call this model vandalism binary classifier. The second model that we are going to compare with is different only by addition of knowledge manipulation semantic features, which are added on top of features used in the first model. So that's why in the picture on the left, we have this part in gray to highlight that this is deactivated in the first model. And the second model just have on top of it additional features used. So the second model is called Enhanced Vandalism Binary Classifier, with the idea that such approach may improve vandalism detection if knowledge manipulation is indeed reflected in revert status flag. We do not explicitly compare our approach to ORS or LiftWing, which is current Wikipedia automatic vandalism detection system. Why? It contains multiple components and it's run in dynamic environment by utilizing microservice architecture. So for sake of the experiment, we have only duplicated one of the components of LiftWing, which is presented on the left. So in other words, we have simplified this component, which was in charge of vandalism detection, and duplicated in our work and then built on top of it to compare. So we moved to data analysis stage. In the first step, we have investigated if there are any differences in edit patterns between fork and Russian and Ukrainian Wikipedia. we have discovered that fork contained prominent sites of content modifications, like not similar to patterns in Russian and Ukrainian Wikipedia, such as remove action are highly more frequent in fork case. Next, we have detected edits in the scope of Russian Wikipedia and fork, which were similar between each other. To understand which ones are similar, we used Levenshtein distance calculation with similarity ratio exceeding 60, which was set to this number based on previous research by Trofimovich, who worked on Russian Wikipedia fork dataset investigation. So inside this scope, with similar edits, we wanted to analyze how frequent it was for Russian Wikipedia moderators to revert changes in the scope and outside of the scope. So we have discovered that revert rate in the pages scoped to revisions that are similar to fork is much higher, which is 0.64. And revert rate within scope of other pages is 0.18. We also wanted to understand what is the nature of the differences in the text removed and inserted into fork compared to text in Russian Wikipedia. To do that, we conducted Jensen-Shannon divergent shift analysis. This measurement, on this picture, we can see that we compared two texts. And I do not insist to try to read the words here, so we will analyze the examples in this slide. So we have discovered that narratives removed from the fork represent geopolitical conflict, Ukrainian and identity. So they remove Ukrainian identity and governments-related words. They remove references to Ukrainian territorial classification and institutional entities as well. So this systematic removal of terms suggests an intent to sanitize or obscure terminology associated with Ukrainian sovereignty and the framing of Russia as an aggressor. From the other side, the vocabulary inserted into fork tends to reframe the same geopolitical issues through the lens of federational integration, regional autonomy, attempts to legitimize acceptance of different region to Russia. Dominant terms include territorial classification and affiliation with Russian identity. Those insertions contribute to a shift from military occupation to peaceful political affiliation, aligning with the strategic narrative promoted by Russian state. Based on the words that we have found during the Jensen-Shannon divergent shifts analysis, we have conducted an investigation of different frames inside Russian and Ukrainian Wikipedias. We set up that baseline frame can be represented by words such as invasion, occupation, and aggression. Shifted frame includes words such as liberation, special operation, and referendum. The FIDF scores analysis has shown that while baseline frame seems to be similar for both Russian and Ukrainian Wikipedia, shifted frame words has bigger score in Russian Wikipedia. This may suggest that Ukrainian Wikipedia is not attacked with attempts of knowledge manipulation to the same extent, or at least in the same form, which we can see inside Russian Wikipedia. So during evaluation stage, we have divided evaluation dataset into subgroups by language and by topic in order to analyze separately subsets of data related to pages which we can see also inside fork and other pages which were not there. The goal is to see whether features that were specifically engineered to detect manipulation improve performance in detecting vandalism. As we can see, the performance of manipulation of our classifier increases such metrics as Braille score and Cohen's kappa while IUC F1 stays relatively similar. Yeah, so we took a more detailed look at few metrics because we wanted to understand actually, even if our model is not the best and not better in terms of IUC, for example, maybe there is something else in there which makes it more calibrated, for example. So we compared between models and subset how much their predictions outperform random guessing with taking into account labeling balance by using Cohen's kappa. We present results with confidence intervals in order to highlight that given measure display improvements in manipulation-aware model, especially in Russian setting. We also compared how close the predicted probabilities were to the actual outcome by conducting Bayes score. In this measure, we, in manipulation-aware model, indicate better performance in comparing to vandalism-only classifier, again, in Russian setting and in Ukrainian full, not limited to fork topics. Final evaluation stage included an attempt to answer the question, can we generalize? And in order to understand, the derived approach, we used propaganda corpus in the same pipeline. It has resulted in F1 score 0.91. And in this case, what I want to highlight that we compared between itself. So we compared vandalism-aware only model, manipulation-aware only model, and combined vandalism and manipulation-aware model, so to make sure that we do not miss understanding if manipulation of vandalism itself is already good enough. So to conclude, answering research question 1, we found that a subset of edits in Russian Wikipedia share linguistic and framing patterns similar to those found in the manipulated Russian Wikipedia fork. This highlights the need for greater attention from Wikipedia patrollers and automated tools. To answer research question 2, we can say that Russian Wikipedia fork-based signals enabled us to train manipulation-aware models. Those models show stronger calibration. They are more confident in their predictions. To answer research question 3, we highlight that the model generalizes across both Russian and Ukrainian, and more importantly, they achieve good results on external propaganda corpus. This suggests potential for cross-domain detection of manipulation, even outside Wikipedia, but it requires additional research. As future work, we see several directions. The first one, incorporating rating-based annotations, which could help capture nuanced form of knowledge manipulation, because we understand well that some knowledge manipulations are embedded inside revision itself. So revision may contain multiple changes, and knowledge manipulation may be only one small part of it. We also plan to expand the Russian Wikipedia fork dataset to support a wider range of research in this field. And additionally, this work could benefit from integrating fact-checking systems. We also acknowledge some limitations of this work. For example, using reverted status as proxy for knowledge manipulation is indeed weak approximation and may not always reflect editorial intent. Our current study is limited to 2 languages, which may not fully generalize across multilingual context. And finally, we acknowledge the potential misuse of manipulation detection models in adversarial setting. These models could be analyzed and adapted to improve future manipulation techniques, but this only is the reason why we have to show these limitations and make sure that we can work towards improving such methodologies. I want to highlight that 30% of my tuition fees were covered by Grammarly, and I would like to thank them for making this work possible. And computational resources were provided by Denova, company, and big thanks to them for making this research much faster. I guess, yeah, I'm ready for questions.
I'd like to start. So I can start. I'm curious. I'm curious about the possibility of detecting these manipulations automatically, and maybe based on your like related work research, are there like fully autonomous systems, or do they, for example, require a human in a loop to be more confident and to correct for imperfections?
Okay, so inside Wikipedia setting in general, the vandalism detection automation system doesn't work like instantly label any revision like forbidden or something like this. So there is definitely a human in the loop inside Wikipedia system. So that's why when we move from vandalism to knowledge manipulation with this even stronger accusation to person who delivers these changes, we should have human in the loop. So this is just normal. And this system aims to be only supportive for those editors who may potentially use it.
I see, thank you. My next question is that your work focuses primarily on textual changes in edits, and could incorporating other data sources available on Wikipedia, such as user metadata, edit history patterns, source citations, or discussion page content, further improve the detection of subtle knowledge manipulations? And what challenges would this introduce, particularly for generalization beyond Wikipedia?
Mm-hmm. So basically, when the data was collected, we have removed everything which was not text-related changes. And this results in having like, I don't know, maybe below 50% of data removed. So this means that a lot of changes indeed are related to links changes. For example, there may be a separate direction to analyze like links reliability or references reliability and etc. So this is really important research, and it probably will not generalize well on other settings, but I suppose it's fine because we still want to focus on Wikipedia because Wikipedia is widely used by many researchers. And as I remember, we even here had another master thesis focus based on Wikipedia data set. So making Wikipedia safe brings us more value.
Yes, but my question is that Wikipedia may have other metadata complementary to text. Why not to use, for example, user metadata or something like that? Is it possible to use that? I don't know, some behavioral patterns or something like that.
Yeah, I understood now. Thank you. So in this research, I deliberately removed user information from features list because I didn't want to introduce bias based on the, for example, factors like anonymous user or not anonymous user. And this may be a problem because we don't want to create a model which just penalizes all people who are anonymous because they may include valuable information to Wikipedia, but at the same time, they may be like threatened by third parties for doing this. So that's why I didn't focus on these features. But technically, yeah, it may, in some setting, it may bring even better results.
By the way, I'm asking the question from Notebook LM because we run all of your works through the model, and I was just curious what the questions were produced, and of course I refined them myself. And the second question is also from Notebook LM. Your core models rely on BERT-based architecture for text processing. What are the potential limitations of this architecture for specific task of detecting subtle semantic shifts, like knowledge manipulation and so on and so forth?
Okay.
What's your intuition?
My intuition is that I'm afraid it can remember certain framings introduced by Russian Wikipedia fork, and that's why it may be not well not be replicable as well to settings with other types of knowledge manipulation. So we focus here on specific deliberate attempts of Russian government to introduce specific direction of narrative. So I assume that that may be a limitation in this scenario.
Okay, thank you.
While passing mic to Vadim, I just want to ask, you mentioned this, I understand that Russian fork is that when they created this, their sovereign Wikipedia, right?
Yes.
And what is Ukrainian fork?
We don't have Ukrainian fork. We use only Ukrainian and Russian official.
But can you get back to the charts? And there was like 4-bar chart, and there was UA fork.
Oh, this
UK
is
fork.
like pages, which in fork, we don't have all the pages of the Wikipedia, which are like, they match only on a limited number of pages, few thousand. So that's why we wanted to check metrics in the scope of matching pages and in the general scope as well. Matching to fork, Russian Wikipedia fork, yes.
Okay, Victoria, many thanks for your work and for a nice presentation. I'm not using this notebook. I would like to offer you to have a dream. To have a dream based on the anticipated future work. Could you please go to the future work?
Yeah.
Yeah, future directions. Granular labels, rating-based annotation, and nuanced manipulation. That's interesting, but a little bit too much technical and narrow-scoped within Wikipedia. Expand RW fork using semantic search to include more manipulative examples across multiple language editions. Multiple language editions is great. Combined with fact-checking systems, that's nice. I would like to suggest looking into the social media sources you mentioned, including X or Twitter, as we prefer to call it, and also to look into the domain of event prediction. Do you think there would be a sort of correlation with the peak of manipulation and the probability of a certain type of events in a certain geographical region?
Yeah, for sure. And in our work, I didn't highlight here because of limit of time, but what we also did, we tried to we created embeddings of edits, Russian, Ukrainian, and fork, and we tried to find similar embeddings between those three sources, because when we conducted Levenstein distance, it's obvious we can conduct it between Russian and Russian, but we cannot conduct it between Russian and Ukrainian. So that's why we created embeddings and tried to find similar edits. But we used this only to analyze temporal activities. And we found that like in similar embedding edits, there were spikes in activities during, obviously, at the beginning of war and during some other events that we didn't match to special historical events, but it was visible that there are spikes in certain periods of time. So for sure, there are spikes related to what happens in the world in them.
For example, I would offer you to evaluate what's the probability of orcs going into Lithuania in the near future, based on the manipulations which are popping out currently, by the way.
Yeah.
Victoria, thank you very much for your presentation. My question is, do you think it's possible to also track the visual content changes? Because not only we can manipulate text, but also by replacing pictures or graphs or any visual data, it's also very, very huge source of manipulations sometimes.
Yeah, for sure. Actually, in the related work, a few people state that there is a gap in finding manipulation, especially in Wikipedia, when pictures are changed to introduce new narratives or new biases. I think that it can be started from simple things like analyzing picture itself and seeing what is changed, and to more advanced things, but I wish it could be possible, yeah.
I want to jump back to your model selection. Can you justify why you selected those specific models?
Yeah. So basically, as I mentioned here, Wikipedia has this lift-wing system, which is quite huge and it handles a lot of things. And inside this, there is vandalism detection module. And this module is based on Google BERT uncased model and cat boost classifier. And that's why we took it as basis to try to replicate. It's kind of toy example of replication, but we tried to replicate it here. That's why we use the same models.
Thank you.
Yeah, speaking about modeling, what is exactly the prompt structures that you feed into BERT model? Is it like only change comment, or is it like before and after?
Sorry, I'll list slides. Okay. So basically, when we talk about Russian Wikipedia fork, it's quite simple. We just have the chunk of the text which we want to label like manipulated or not. When we talk about vandalism detection, we actually divide the process based on the type of the text. Like text may be originated from inserted, remove it, change it, or it may be page title. When we talk about inserted and removed, it's kind of clear because we just have text which was inserted or removed. It becomes complicated when we talk about changed. In this case, we took like a simple path. We just combined it, text before and text after, and then used this.
And have you considered adding not only like before and after, but some context, like, I don't know, summary of the article or article title or something else?
Yeah, I understand this question, and this is something that at first I considered, but it was too heavy to do, and we didn't have all the information about the article in the dataset. So dataset, you can imagine, is as chunks of changes. It doesn't have the whole article itself. So if we want to conduct such study, we have to collect all the articles, do the summarization, and then use it.
Okay. And not a question, but a suggestion from my QNLP shared task expertise is you should consider using GEMMA models instead of BERT because it will work much better. Thank you.
Okay.
Yeah, I just want to add that in your list of literature review, there were at least 2 master theses in past in our program. So last year it was detection and analysis of manipulation techniques in news channels on Telegram by Volkova Natalia. And the year past that, in 2023, it was another thesis about computational analysis of dehumanization of Ukrainians on Russian Telegram by Katerina Burova. Obviously, it's another source, but I think it would be great if you can mention them in your work. Thank you.
Thank you.
Okay, we don't have questions anymore. Thank you, Victoria. So now we will have a lunch break till 1:20 p.m.